Imagine standing near a campfire on a cold night. The side of your body facing the flames gets hot, while your back stays freezing. That heat transfer relies entirely on a direct line of sight. If the fire can't see your back, it can't warm it. In engineering, we measure this unobstructed pathway using a mathematical term called the view factor, written as Fij. It tells us exactly what fraction of the total radiation leaving one specific surface goes directly to another surface, like you. At this stage, view factors are defined entirely by the spatial relationship between surfaces. The actual temperatures or the materials the surfaces are made of do not matter at all. We are only concerned with shapes, angles, and distances. Let's look at what we call a diffuse emitter, a surface that gives off heat equally in all outward directions. This brings up an interesting question. Can a surface radiate heat back onto itself? On the flat plane surface, all pink heat vectors point outward. Because it cannot hit itself, F11 is 0. The same applies to the convex surface curving outward. Heat spreads away, so F22 is 0. But in the concave bowl shape, outward firing arrows hit the opposite side of the same surface. Here, F33 is greater than 0. Simply curving a surface inward creates a physical trap for its own radiant energy. The geometry alone dictates how efficiently the shape dissipates or retains heat. When calculating heat transfer between two separate objects, there is a common trap. If surface 1 sends 50% of its heat directly to surface 2, it feels logical to assume surface 2 sends 50% back. This diagram shows why that assumption fails. Panel 1 is huge, so half its radiation reaches panel 2, making F12 exactly 0.5. But panel 2 is tiny. It scatters light everywhere, so only a tiny fraction hits panel 1. To mathematically balance this, we use the reciprocity rule. You multiply the area of surface 1 by its view factor, which will perfectly equal the area of surface 2 multiplied by its reverse view factor. You have to account for the effective shining area. The physical sizes of the areas act as a strict mathematical scale. This rule ensures we never violate the conservation of energy when tracking radiation back and forth between disproportionate objects. Let's test these rules on a specialized closed geometry. This diagram shows two concentric spheres. Surface 1 is the inner gray sphere, and surface 2 is the outer pink sphere. Take a second to deduce the view factor from the inner sphere to the outer one, F12. Because the inner sphere is entirely encapsulated by the outer sphere, 100% of its outgoing radiation has no choice but to strike the outer wall. Therefore, F12 equals exactly 1. Now we can use the reciprocity equation to find the reverse path. We substitute a 1 for F12 and immediately see that the reverse view factor, F21, is simply the area of the inner sphere divided by the area of the outer sphere. This demonstrates that even in closed systems, we don't have to calculate every interaction from scratch. If you can logically deduce just one guaranteed view factor, the reciprocity rule allows you to solve for the reverse pathway mathematically. So far, we've looked at individual shapes and pairs of surfaces. Now we scale up to a completely enclosed room. Look at this sealed 3D box. If we track all the radiation leaving the base, surface A1, every single ray must eventually strike the top or the sides. There is nowhere else for it to go. This gives us the summation rule. The fractions of radiation leaving a specific surface and hitting every surface in an enclosure will always add up to exactly 1. An enclosure creates a perfectly closed mathematical loop. By knowing the total is always 1, we guarantee that no energy escapes our engineering calculations. Let's consolidate everything into 4 core rules you can take into your next problem set. First, view factors are defined by geometry, ignoring temperature entirely. Second, flat and convex shapes cannot view themselves, while concave shapes do. Third, the reciprocity rule uses area to balance the math between disproportionate objects. And fourth, the summation rule ensures all fractions inside a closed box add up to 1. These 4 rules provide the necessary framework for all radiation calculations. You must master this geometric baseline before you introduce variables like surface temperatures and material properties.